Hello and welcome to Earthquake Tip number 5. My name is Dr. Shailesh Agarwal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to understand language to our professionals who are in the field designing and constructing structures, especially architects and engineers. But before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. This earthquake tip will explain you how do structures behave during earthquake. But before we get into the earthquake tip, you are aware that earthquake causes shaking of ground, and therefore any structure of building resting on ground will experience motion at its base. And that is shown in this figure. It is learned from Newton's first law of motion that even though the base of building moves with the ground, the roof, being heavier, has the tendency to stay in its original position. This roof is connected to the ground through walls and columns, which try to drag the roof along with them. Let's understand it with another analogy. When you are standing in the stationary bus and the bus is suddenly started, your feet move with the bus, but your upper body tends to stay back, making you fall backwards. Same thing happens with the building. Your upper body is like a slab and your foundation is like your feet. This resistance shown by the structure is known as inertia, and it acts in the opposite direction of the movement. As you can see here, the ground moves in the right direction, whereas the building moves towards left. Now let's see in this figure 2, which shows roof is supported by these columns. So when the ground moves like this, the building is thrown backwards and roof experiences the force due to its inertia. And this force is called inertia force. According to Newton's second law of motion, this inertia force is equal to mass of the roof, let's say capital M, multiplied by the acceleration which the ground experience. So the inertia force equal to mass M into A acts in the opposite direction of ground shaking during earthquakes. So remember, more mass means higher inertia force, means heavier buildings will attract more forces during earthquakes, and therefore lighter buildings sustain the earthquake shaking better. This inertia force generated in the roof is to be transferred to the ground through these columns. And this inertia force causes forces in these columns. During shaking, columns also undergo relative movements between their ends, which is shown by the quantity small u in this figure. The larger is the relative displacement, that is u between top and bottom of the column. Larger will be the induced force in column. Also, stiffer is the column, means having larger size. Larger will be the force induced in the column due to earthquakes. This internal force in the column is also known as stiffness force, which is calculated as stiffness of the column multiplied by this relative displacement between its end, which is denoted by small u here. So in summary, we can say during shaking, the inertia forces developed, which is to be transferred to the ground through beam, columns, and walls. Now let's have a look at this figure, which shows that earthquake shaking, as explained earlier, in the earlier tip can be in all the three directions, that is two orthogonal horizontal directions X and Y and vertical direction Z. Therefore, during shaking, the ground shakes randomly in all the directions X, Y, and Z. It means the structure on the ground are subjected to inertia forces in all the three directions during earthquakes. Primarily, the buildings are designed to carry gravity loads. That is, vertical load comprising of building's own weight and imposed load or live load multiplied by the acceleration due to gravity acting in the downward direction, that is minus Z direction. This is called gravity load, and most of the buildings are designed for this gravity load. The vertical acceleration during ground shaking either adds to or subtract from the acceleration due to gravity. Since buildings are normally designed taking into account factor of safety, and therefore most of these structures are found adequate against this vertical shaking, whether it is in plus Z direction or whether it is in minus Z direction. However, the horizontal shaking, which takes place in X and Y direction, remains a concern. Structures designed for gravity loads in general may not be able to safely sustain this horizontal force due to horizontal earthquake shaking, and therefore it is necessary to ensure adequacy of structure against these horizontal forces due to earthquake. Let's move to the next figure, which shows the horizontal inertia force which is generated at the level of mass of the structure, usually at the floor level. These horizontal and lateral inertia force are transferred by the floor slabs to the beams, walls, and columns, and then to the foundation, and finally to the soil underneath. Therefore, each of the structural elements, that is floor slab, beams, wall, and columns, and foundations, and the connections between them must be designed to safely transfer these horizontal inertia forces through them to the ground. That is the philosophy of flow of earthquake forces. Normally, the vertical elements, which is wall, columns, are the most critical elements in transferring these inertia forces. However, in practice or in traditional classical gravity load design, floor slabs and beams are normally kept thicker and heavier than your walls and columns. Also, the walls are relatively thin and often made of brittle material like masonry. These walls are poor in carrying horizontal inertia forces along the direction of their thicknesses, and therefore they fail during earthquakes. Let's have a look at this figure, which shows in the top failure of a masonry wall during earthquake due to inadequate thickness of that wall, whereas bottom figure shows poorly designed and constructed reinforced concrete columns can also be disastrous. The failure of ground story columns resulted in numerous building collapses during 2001 Bhuj, India earthquake. That's all about this earthquake tip. You can download this earthquake tip from www.bmtpc.org. The next earthquake tip, which is the tip number 6, will be on how architectural features affect buildings during earthquakes. Thank you very much.